because section 1 and 2 are still based on Cartesian coordinate and what we call a Euclidean space. And now 4.3 is to generalize that. So there are a few different steps of generalization. First, you can say you still stay with the same Euclidean space. And first start with a Cartesian coordinate. And then you define another coordinate that is not non-Cartesian. Basically transform XYZ to new variable and for instance QR QI is 1 right we need to wait just 1 2 and then stay with 3-dimensional space, or if you want you can generalize to higher dimensional space, doesn't matter. And so QI, the QI depends on XYZ or what you call X2, right? And these are X are the Cartesian coordinates. So yeah, you define a function. So these Q sub I are your new coordinate variable, and they are nonlinear. And so whatever we did in section 1 will not work. The linear transform, because we use linear transform. The transformation from X to X sub I or to Q sub I are non-linear, so you cannot directly use the formula. So we need to generalize that to a new set of formula. So, so that will introduce new language and new quantity. So that is our starting point. So that is the first step, first generalization. You generalize the new non-Cartesian coordinate, still Euclidean space, and that will make it clear that the language that we introduced in the section 1, the covariant and contravariant vector, all that becomes useful, because in Cartesian coordinate, those are redundancy, because the contravariant is covariant, they are the same. So you don't understand why you just go through the trouble to define these things. But at least even in this level of generalization, you need to separate the two. They're not the same now. Generally, they are not the same. The contravariant component, covariant component, and unit vector also, they are not the same. So we need to separate that. So that's the first way of generalizing this. Another generalization is you stay with Euclidean space, but now you restrict yourself to maybe a subspace. Like in 3-dimensional space, we can say, originally the geometry is just a 3-dimensional Euclidean geometry, but if you restrict yourself over a subspace like a surface, arbitrary surface or regular surface or spherical surface, whatever that. So the surface obviously reduces the dimension, it's 2 dimensions. Also, because it's a curved surface, obviously you cannot define a global Cartesian coordinate on the surface. So that becomes a necessity to use the language that we just defined. So the language over here at first is just our choice of arbitrary general coordinate system, which is not necessary. You stay with a Cartesian coordinate, you can still work on that, work out everything. But if you like you can use a spherical coordinate or cylindrical coordinate for convenience, but that is not totally necessary. But if you stay with a curved space, even though it's within a Euclidean space, sometimes you want to work on the geometry based on the parameterization of the surface. You don't want to always go back to the outside the space or what this surface embedded to a 3-dimensional. That's 2-dimensional surface embedded in the 3-dimensional Euclidean space. But that is sometimes not convenient to do that, because you do that, you always need to specify your S. Yeah, there's a equation you need to satisfy. All the points on the surface, you need to satisfy a certain equation, and that can be cumbersome. So, uh, many situations you want to work on the surface itself. The surface, uh, to, to work on the geometry in a curved surface, then the language is is pretty much the same as what we did for the non-Cartesian coordinate. We can use the same language to describe a curved surface, right? And so that is a application beyond just change a variable. And then finally, another step of generalization is that we might actually work on a space that may or may not be embedded in a Cartesian higher dimensional space, and then it intrinsically is curved, and we can using this kind of language to describe it and actually define how how to uh, how to say it is curved or not curved. It's quite non-trivial to say that. It's actually beyond our discussion. I mean, to see whether space is curved or not, you need to go in the finding the curvature, which is, your textbook is stopped at the. It didn't actually go that far to calculate the curvature, right? But that also can use this kind of language that we are about to develop. Okay, and then and in that case, then you may not have this Euclidean space that you can fall back to, except locally. Locally, you can always find, say, a surface. You locally, you always find that you can find a locally, it's like a two-dimension plane, um, that on this local plane on the surface, you can define your Cartesian coordinate locally. But that is not global. If you go further away, that coordinate system is not good anymore, right? So we can uh, in intrinsically non-Euclidean space, and we must use this kind of language. And some of the discussion we go through is just to develop the language, and after we develop the language, sometimes we forget. We'll not go back to the development. Say for example, the first you define using this new coordinate system, you define the unit vector according to a transformation to the Cartesian unit vector. But if you don't actually have a global unit vector, Cartesian unit vector, sometimes you are not actually doing that. Okay, so we'll get on with that. So yeah, these are Cartesian coordinates. So let me write down. So in assuming we have a Cartesian coordinate, so x, but write explicitly first. That's what we already seen in section 1, and using the notation that we did the contravariant coordinate multiplied by covariant basis. This is 2, 3, or using Einstein notation, it's 1. Right, that's the spatial vector, right? Now we want to develop define unit vector using your Q as your coordinate, and the way to define it is first this epsilon is, you can say epsilon. This is epsilon's and actually we define the covariant basis first. Later we'll also define the countervariant basis. We define the covariant basis as just the partial Q, the actually Q sub I in the superscript. This is a countervariant coordinate Q sub I. Yeah, so actually let's say this define this I first and then the X. But it turns out that it's just like a transformation that we define. If we substitute all these coordinates here, so it's just substitute this into that, this becomes minus xj. So basically, this is like a transformation. Remember, we talked about this is a covariant quantity, so you transform like that, assuming that you have x of I and transform the q of I. This is becomes a transformation matrix, but this transformation matrix is not a constant, unlike it's not a constant number, unlike in section 1. All these are just a constant number. Right? Remember that this is just the dot product between the unit vector. But as now this is not number. These are function of space also. Remember this this transformation matrix now becomes a function of space, but we can still using that to transform the old Cartesian coordinate, which is global. This doesn't depend on space, but now using this transformation to define a set of unit vector that depends on spatial position, right? So this is a function of if you want, this is also a function of Q, or the Q1, Q2, Q3, right? But it transforms it like that. All right, and now the difference between the section 1 and now is that we cannot transform the coordinate. You don't have a linear transformation to transform all these coordinates, right? You can only transform it infinitesimal. So x is like you cannot transform it to a vector that is using linear transformation to a combination of all these q's of I and turn this unit vector. It doesn't work like that. You can only transform a change of x. So if you have x, and but you have another x at how do you say x prime or whatever. But if you can say this express delta x. So you have x is delta x. So you can only transform this over a delta x, right? At the location. So whatever this x this vector starting from any coordinate system, because this is your origin. From here to there, the function is not linear, so it changed. The transformation matrix changed from here to here, so you cannot transform the whole thing, right? You only can transform locally. So if you have a delta x which stay with a certain local position, then at this local position you can do a transformation just like here. But we'll use the covariant because that we can write now this delta x over dx. We can write it like originally that in the Cartesian coordinate this is dx, right? And then in the new coordinate system becomes a dq epsilon. Right? This is not unit vector, so be careful. This is just the basis vector. It's not unit vector because it's not normal. Right? Because you define like that, this may not the length of that may not be 1. Okay, and now we know how to transform the basis. Then this how to transform from dxi to dqi. we need to make sure that this equation valid, right? And the transformation actually quite straightforward. So this is just dqi. It's just like how you calculate a differential. dqi is just this partial qi. Okay. Right. And this is like how you transform a conjugate in what we discussed in section 1. I transform a contrarian component, right? This is exactly the same transformation, but you can also look at this as how you do the calculus, how you calculate differential. The differential of this qi function when you vary the function that depends on x, assuming it depends on x, or the xi, or the x1, x2, x3, then you just take the derivative of your quantity divided by x, whatever x1, x2, x3, and multiply the differential x1, x2, x3, and sum over them. That's the usual way of doing calculus, doing derivative. And it turns out to be exactly the same as the transformation rule of contrarian component. Okay, now we can check that this object will produce this one. Say PQI epsilon I. Now let's just copy this thing. So partial Q xj, right? And then the other is this epsilon. So it's this one. So partial qi, because we sum over I also. So choose I here, but that we cannot use j. We already use j here. So this becomes okay. That is a unit. This is capacity, right? Now we realize that this is like the sum of I, right? This is sum of I. This is like the chain rule, and that becomes a partial xk, partial xk, xk, right? But this combine these two factors becomes this one, because that's how you do the chain rule and doing partial derivatives. Yeah, and you know that these are Cartesian coordinates, so this derivative is just conical delta. Delta kj and xj. Okay. And okay, and you actually do sum over both, but you sum over one of them, you use the conical delta, so you sum over k, that becomes xj. Okay, so that is what we set out to do. So that's equals to that. We show that if the basis vector transform like that and the coordinate transform like that, then this equation where is valid. So this change a little bit over a location, a position vector, then you can express as the O Cartesian coordinate, and also the new generalized coordinate system this way. It's okay. So that's how we do it. And now the next thing is this is just the beginning. 10 minutes. Okay. And now we can define. We can calculate something else. Like according to just following your textbook orders. So the next equation is just once we have the basis, we can express any vector using these bases. And see if you have vector A, then we have some base. The contrarian component times covariant base. Right. Yeah. Good. And by the same discussion, you know that all these countervariant components at the given position will be, we need to transform like a counter. If it is a vector, we need to transform like this one using the countervariant vector transformation. Okay, so that's just that equation. Now we want to calculate the displacement, not just the displacement vector. We want to calculate this as norms. We got there. Define it as something. It doesn't have the. So this ds is what we have in this dx. This we might as well say where the term is dx. ds. Right. This this is what you call ds. Right. You want to know the square of that actually, and that is a little bit misleading if you want to generalize that the square or sometimes are always like positive, but later on we'll generalize to if we discuss general relativity and either special or general relativity, that ds squared can be negative. It depends on whether it's space-like and time-like, this difference, and then whether you use what convention you use to define. But we'll stay with this square notation anyway. So just we remember that this later on we generalize that it may not be a positive, it must not necessarily a positive value. So this is just using that. So just use that. So obviously in the Cartesian coordinate you can say it's just this dot into itself. So it's just dx square. Now you need to get back the summation explicitly, right? You use O1. And the new one is a little more complicated because you dot into itself. We actually haven't defined a dot product yet, but you use the old way to define your dot product. Or just like one vector dot into itself, but then the vector is expressed as this one. This is a differential vector. But then you dot into itself, we cannot use the same I. So we need to use another index like dqj sum. Right? And then just take out all these coordinate differential. And then what we left is this object which we don't know what it is yet. And this dot into itself. This base, one basis dot into another basis. We don't actually know what it is, and we just give it a name when we don't know it. So we just give it because it has two indices, so it is the object with two indices, the I and J, J, and this equation is sum over I and J, or contraction of I and J, right? And then later on we will show that this transforms just like a covariant index, covariant variable. So so you can identify this as a covariant second rank tensor. And that we probably have a later discussion on that. Okay. If we can actually write down the transformation. This is just like this one, right? This covariant object is transformed like that. So let's just write out how you transform it. So, or we don't have to write out. We can actually use the definition here. Epsilon I, epsilon j. So let's work it out. Okay. Epsilon I dot in epsilon j. Epsilon I is this one here. but we cannot use J. So, okay. So this is one of them, epsilon I, and then dot into epsilon J, right? So in J we change that to J, and now we cannot use the K. That's XL and EL, right? We can do that, and now we can write it down. Just take this transformation matrix out of positive. Okay, other QI, XL, other QJ, and EJ dot into EL, right? Now this looks like a transformation of second rank tensor. So you transform this second rank tensor to this one by this or this two transformation matrix for covariant variable, right? And so that looks like a tensor. And this object, if you stay with Cartesian coordinate, call this a Cartesian coordinate unit vector. And this dot product is just our usual dot product between in the Euclidean space, and this will be just your conical delta, just like delta I. Both are not that is in all in subscript because you have superscript. You need a sum over k. But if you use that to do a sum, or you can write down the explicit explicit quantities for Gij is this two transformation matrix and this sum over this the two superscript k, right? And if you realize that that is both are called the transformation matrix. If you go back to if Q is not a generalized coordinate, so it's just another Cartesian coordinate, what we call x prime, right? This object will be also a conical delta. Do you remember we talked about this? If remember that if this is Q is x prime, that would be conical delta. Remember we talked about that? Remember some of you, we talked about, I think that it's the first discussion of section 4.1, this kind of transfer of this Cartesian coordinate and another one you just rotate or whatever you do with the linear transformation. That one has the property that the transformation matrix, what we call it A or S, and this is like a multiply the matrix with its transpose because you sum over the same index, right? This is multiply its transpose, and we show that the transfer actually is equals to the inverse. So this is S and S inverse. Identity matrix. Yeah.
You have the xk and xl.
This is I'm saying that if Q are not generalized coordinate, I just go back to another Cartesian coordinate, then this object would be just a conical delta. If it's not obviously this is not a conical delta, I'm just saying that why we have this kind of expression. If we just go back to what we discussed in section 1, then this object, whatever we define as G, is simply a conical delta. But for non-Cartesian coordinate or generalized coordinate Q, that would not be the case.
Yeah, I get it.
Yeah.
Now, like the superscript has to be the same, so that would be conical delta to valid. But for our case, we find we have the superscript k, and so in that case,
no, that's not true. About that case,
Yeah, this is sum over k, sum over k. Your ij are the index in Gij is sum over k. This is like a product of matrix product, except it's sum over the same index, which means according to the matrix multiplication rule, you need to do a transfer of one of them.
Okay.
Like do a transfer of the second one, then this matrix time is transfer.
That is cool. But now, in case now, we have like when in our initial case, so we don't assume that. We just
Yeah, well, with G, you don't assume that. We don't have that. This is a discussion. Say we go back to the old case, what we get for G. So you're just saying that the G for a Cartesian coordinate will be a Kronecker delta. Is that okay? That is just going back to the point that going to so it becomes trivial. So this is what you call the metric tensor. And in many the discussion, the G is a central object in discussing the geometry, either the generalized coordinate or generalized space. That is central. And but obviously, we go back to the trivial case, the Cartesian coordinate in the Euclidean space. Then this object becomes trivial again because this becomes a Kronecker delta. Okay, this is just a discussion showing that using this transformation rule, which is general, this is a general. And going back to the Cartesian one, then Gij is just Kronecker delta become trivial again. Is that okay? I think I've been out of time. Huh? Oh yeah, a few minutes out. Okay, I thought I could finish that, but anyway, hopefully we'll get more done next week. Okay, I stop here.